Hi class, topic B5, gravitational force near Earth's surface. Previously we mentioned the force of gravity, and let's talk more about this force. So the force of gravity is an attractive force between any two objects with mass, and another name for Fg is weight. When we are close to Earth's surface, we can calculate this force using the equation here, Fg equals mg. So force of gravity equals mass times acceleration due to gravity. And recall in previous parts of this course that g is a constant of 9.81 meters per second squared down. In the region around the Earth, we feel an attractive force of gravity, and we can map out the direction and strength of this force in something called a force field. Any object with mass placed within this region will feel Fg. In a force field, the arrows of the lines tells us direction, and the spacing of the lines tells us strength. So notice the direction of Fg is always towards the very center of the Earth, and the strength of Fg depends on how close you are to Earth. We can only use 9.81 meters per second squared in the previous equation, Fg equals mg, if the other object is near Earth's surface. And what happens at other locations or planets? The strength of this force field must be different. So let's rearrange that Fg equation to isolate for small g, and we get the gravitational field strength, or how much force is pulling on 1 kilogram mass. Notice the units of g are also newtons per kilogram, and those are equivalent to meters per second squared. So when you have to report gravitational field strength, the preferred units would be newtons per kilogram in this unit. However, meters per second squared is also valid. Gravitational field strength is given the letter small g. And we can see that actually we would learn in grade 12 that this constant 9.81, it depends on the mass of the planet and your distance from it. So if we're near Earth's surface, we can say your distance from the center of the planet is the radius of the Earth, which is why we can say it's a constant as long as we're close enough to the surface of the Earth. And because of this dependency on mass and distance to the center, different G values will exist for different planets or different locations on Earth. So let's try an example. An 82 kilogram astronaut on the moon experiences a force of gravity of 131 newtons. What is the gravitational field strength on the moon? So drawing our free body diagram of a person on the moon, they're not accelerating up or down, so their free body diagram looks the same as if they were at rest on the Earth. Fg down, Fn up. 131 newtons down and 82 kilograms are the two givens. Our equation for field strength, Fg over m, gives us our field strength. So we substitute in 131 newtons divided by 82 kilograms, and we get 1.6 meters per second squared down. So now let's look at the gravitational field strength around the Earth. The Earth is not perfectly spherical. It's actually fatter around the equator due to its spin. So this force field field exists all the way to the center of the Earth. And notice, for example, that the distance from the center to the North Pole is smaller than the distance from the center to a point on the equator. So if you're closer to the center, you have a greater field strength. So at the North Pole, you would expect to have a greater field strength because you're closer to the center. Let's look at how G varies with latitude. So as latitude increases, the gravitational field strength also increases. And when you're increasing latitude, you're getting further from the equator. When we increase altitude above sea level, so we're climbing a mountain, we're going higher up. As we increase altitude, we increase field strength, or we decrease field strength. So there's an inverse proportional relationship between altitude and field strength. So let's do an example to demonstrate that we understand the effect of altitude and latitude on, and maybe other things, on gravitational field strength. So example, this is an example in your student notes package. Diet plan for science geeks. The cover of popular magazines often include various methods to lose weight fast, many of which are temporary. Use your understanding of physics to explain 2 ways that people can be guaranteed to lose weight. Explain why these work. So the key word here is that weight. So we want to lose weight. It's a force, and it depends on mass and field strength. There is no need to lose mass. You're perfect the way that you are. So let's look at how we can lose weight by decreasing small g. So pause this video right now, and I want you to see if you can recall the ways that we said you can decrease small g. Okay, so if you said you could move to a higher altitude, so top of Mount Kilimanjaro, that would decrease g. You could say you move closer to the equator to decrease g. You could move to the moon or a smaller planet, and those are all ways that you could decrease g. Mass is different than weight. Mass describes the quantity of matter in an object, and it's in units of kilograms. And it does not change due to location or changes in field strength. However, weight is a force. We measure in newtons, and it does depend on the location and the field strength. To measure weight accurately, an object must be at rest or moving at a constant velocity. So if there is ever a question where we're going to measure weight, but the object is accelerating, then it's an apparent weight. It's not the actual true weight. So we've got your weight on Earth would be maybe 560 newtons. Your weight on the moon might be 90 newtons, but your mass is always 56 kilograms for this little character here. So mass does not change depending on location. So let's further discuss free fall, which we have introduced in different ways earlier in this course. Let's talk about free fall with regards to forces. So pause this video right now. I want you to try drawing the free body diagram for the 2 objects, the tennis ball falling and the feather falling. Okay, from this diagram of, I guess, time lapse of the tennis ball falling at, maybe this is 0.1 seconds every time the photo is taken. This ball is in free fall. There's only gravity acting on it. You can see that the ball is accelerating. So the free body diagram has to show acceleration down. We'll only have the force of gravity on this object. The feather has reached its terminal velocity because the distance between subsequent positions in the photo, it's traveling the same distance down every 0.1 seconds. So that means there's a constant velocity. We call that terminal velocity. And that is when air resistance, so this should say F air resistance is equal to the force of gravity, and that gives no acceleration. Just to recall that free fall is the motion of a falling object where the only force acting on that object is gravity. Terminal speed is the maximum constant speed of a falling object. Air resistance is a force that opposes motion, and it depends on the shape and cross-sectional area of the object. So let's take a look at this skydiver example. So examining the sequence of free body diagrams at different points in the skydiver's flight, can we tell where the parachute opens? So pause this video right now just to take a close look at the free body diagrams and see if you can guess where does the parachute open. So notice in all of the diagrams, FG remains the same because the skydiver's mass doesn't change. FG is near the Earth's surface. Like G doesn't significantly change for the altitudes of skydiving. For our purposes here, you're pretty much near the surface of the Earth for the whole flight. So G can be the same value. So although FG remains constant, FG is the same size, air resistance does change. It depends on how fast you're going at the moment in time and whether the parachute is open. At A, the skydiver starts falling, there's acceleration. As the person speeds up, there's more air resistance. So air resistance grows until they reach terminal velocity at C. So the person is falling, so they're still moving downwards very quickly, but it's a terminal velocity. They don't accelerate any longer. And then at point D is where the parachute opens, because all of a sudden there is a net force up to cause deceleration. So you slow down from that terminal velocity. And when you slow down, because you're hitting less air molecules in a given amount of time, you're going to decrease your air resistance so that you eventually get to a new terminal velocity. So you're at a new terminal velocity that is much smaller than the terminal velocity when you didn't have the parachute. So read more about this example on page 163 because that's a key example that you should know in detail for future assessments. Okay, one more example, and this would be called an elevator problem. Because you are looking at what would the reading on the scale be if the elevator is at rest, at constant speed, or accelerating. So the motion of the elevator will affect whether the reading on the scale is actually the true weight or not. So when we're doing the reading on the scale, we're solving for normal force. The normal force can be bigger than FG. Usually in this course, it's equal to FG, but usually in this course, we are at rest. So let's highlight our givens and identify what we are solving for. So we're going to draw a free body diagram of an object at rest. We have, this is the free body diagram of the person standing in the elevator. So the FG is the person attracted to the center of the earth. So the force on the person, the attractive force downwards of the earth pulling on the person. And then the scale is pushing upwards on the person, which is the normal force. And that's what we're solving for when we're looking for the reading on the scale. Fn may be a person's true weight. It will be in this case with the object at rest. Object at rest, there is no net force, Fg equals Fn, and to calculate Fn, it's simply mass, 61 kilograms, times G, 9.81 meters per second squared, and we get 6.0 times 10 to the 2 newtons. We do need to express this answer in scientific notation to show two significant figures. For part B, if we're traveling up with a constant velocity of 1 meter per second, the key is that it says constant speed. We actually don't even care what the speed is. Constant speed means Fnet is also 0, Fn is just mass times gravity. Part C is a little bit trickier, and you do have homework, your practice problems that are like this. If we are accelerating up at 1.2 meters per second squared, our free body diagram has to reflect that. Fn has to be bigger than Fg. If acceleration is up, Fnet is up according to Newton's second law. We write our Fnet statement from the FBD, Fnet equals Fn minus Fg. Make sure it's Fn minus Fg since we know Fn is the bigger force. many times we could do FG minus FN when F net equals 0. So we might be in the habit of writing FG minus FN, but remember, it's always the bigger force minus the smaller force so that we don't work with negatives. F net is also equal to MA because of Newton's second law. Therefore, MA equals FN minus, we're going to substitute MG for FG. We have an equation that we can rearrange for FN. Fn is equal to MA plus mg. We substitute in our numbers, and our final answer for the apparent weight, the reading on the scale, is 670 newtons. It does make sense that the scale would read mass times gravity and then plus whatever acceleration upwards. So accelerating up at a faster rate would cause the apparent force to be larger. If you close your eyes and imagine that you're on a roller coaster, or imagine that you're on the elevator, if the elevator suddenly accelerates up, you feel heavier into the floor. If the elevator all of a sudden dropped, you would feel lighter and you wouldn't press very hard into the floor. So it does make sense that if we're accelerating up, the force we feel, the ground pushing up on us, would be greater than if the upwards acceleration didn't exist. So that's 600 newtons without acceleration compared to 670 newtons with acceleration. We do our common sense check. We double check that we have the right number of significant figures and units. Okay, so now it's time for you to do some practice questions. I'm just going to remind you to submit the exit ticket at the end of the exit ticket in the assignment on Google Classroom, just to confirm that you got to the end of this video. And also, when you complete the practice questions at some point this week, make sure to submit those as well. A reminder to check your solutions at the with the textbook solution PDF that I've provided to you on Google Classroom. Have a great day.